Okay, let's talk about the equivalent circuit of a transformer. But what we have already learned is that we have drawn a transformer like this. This is the core. I'm drawing it very simple way, and for an ideal transformer we have shown like this only, and in case of a practical transformer we have added two things, like we have added one, this we called x1, this is r1. Similarly on this side r2 and x2. This is how we have drawn a circuit of a practical transformer, and this is the leakage reactance of primary side. This is the winding resistance in the primary side. Similarly, this is the secondary side resistance and the leakage reactance in the secondary side. This is the actually magnetic flux linkage that does not link to the other coil. That is, this is the leakage reactance, not the mutual reactance. So this is basically contribute to loss. This also contributes to loss. And this current is I1 primary current, this current is I2 secondary current. Similarly, this one is N1, this one is N2, and this voltage is V1. Here the voltage is E1. This is the basically the linked self-induced EMF. This E1 will be in antiphase, that is E1 will be minus V1, or we can say this E1 is minus V1 in the opposite side. In the phasor diagram we have seen already. Here the voltage is E2, that is induced in the second coil, and here is the terminal voltage, the secondary, that we will be getting, that is V2. Fine. Now let's say simpler, we from onward we will not show this core and all these details. We will draw this like this one. We show the transformer in a much more simpler way. This is conventionally done, and this is it, and we show all the things as here we have shown. I'm not writing all this one. This is x1, r1, r2 and x2. Okay. And this is n1, n2, and this is the core. Now for most of the circuit analysis become easy. Circuit analysis becomes easier and simple if all the parameters like x1, r1, all such parameters, if all the electrical parameters are brought to the same side, of the transformer. Like if all the resistance and reactances are in the primary side, or all things are in the secondary side, then the analysis will be easier. So, and correspondingly we will have two different equivalent circuit for the transformer. So let's start with case 1. Suppose in the case 1 we are considering that all parameters are transferred to secondary. So all parameters are transferred to secondary, or we are transferring all parameters to secondary. Also we sometimes call it that all the circuit parameters are referred to secondary. That means that we want to have, from this we want to have a circuit that will be like this. Nothing on the primary side, and in the secondary side we should have like this. So this will be V1, this will be V2 as usual, and this will be basically, suppose we call it R02 and this is X02. that is the equivalent secondary total after bringing this R1 and X1 into the secondary side, and already the R2 and X2 exist in the secondary side, and the total combined effect, the total combined resistance in the secondary side, suppose that is R02, and combined reactance, leakage reactance due to both, due to the primary referred to secondary and the secondary itself, total is X02. Then this is the circuit. Now we need to know that what will be S02 and what will be X02. So we could have drawn, this is the final diagram that we want to have. So if we break it, it is like the primary is as it is, but the secondary we could have written like this one: 2 resistance and 2 reactance. What is this? This is V2. So this is basically already existing resistance R2 that we already have. This is X2 that we already have in the secondary, and suppose the equivalent of the resistance that is there in the primary side, R1, when we bring it to the secondary side, it becomes R1 dash. Similarly, when we bring the reactance X1 from the secondary primary to the secondary, it becomes X1 dash. So this R02 is basically R2 plus R1 dash. Similarly, X02 is nothing but X2 plus X1 dash. That is, R02 is nothing but R2 plus R1 dash, and X02 is X2 plus X1 dash. So now we are remaining with, we need to identify that what will be the R1 dash and what will be X1 dash. So to calculate the R1 dash, suppose for R1 dash, how we get the R1 dash, that is basically we are transferring the primary side resistance R1 to secondary. Before that, let us know that we already know that V2 by V1 is equal to I1 by I2, that is basically is equal to N2 by N1, and we call it K, that is the turn ratio. That we already know, but we need this one, so I am repeating this one. Keep in mind. Okay, now what we want to know, that what will be the R1 dash in terms of R1. So we have R1 and we want to find R1 dash. For that, suppose the primary, what is the primary side loss? Because we want R1 dash to be a value that will contribute to same copper loss, that is winding loss, when R1, what R1 has already incurring. So what copper loss R1 incurring in the primary side? So copper loss that R1 is incurring in primary side is I1 square into R1. Now we want R1 dash to be in such a value that the same amount of copper loss it will incur in the secondary. So in the secondary, R2 dash will incur, copper loss will be I2 square into R1 dash. That will be the copper loss in the secondary. And what we want that same copper loss, that what will R1 dash will generate in the secondary, that loss would be same as as R1 was generating in the primary. So R1 was generating in the primary is I1 square into R1. So if we equate these two, then we will get actually R1. So what is R1 dash? R1 dash is nothing but I1 by I2 whole square into R1. That is basically K square into R1. So that is R1. Now so we already have found out this, so we can write this. R02 will be basically R2 plus K square into R1. So R02 is completely determined using existing parameters. So R1 is, we can remove the R1 and we can put this side R2 plus K square into R1. And similarly for X1, for reactance also, what will be there in the primary side? What is the voltage drop? The same voltage drop should be, the reactance should create the same amount of voltage drop in the secondary. So primary side voltage drop due to x1 is I1 into x1. Now, when this I1 into x1 is referred to secondary, what will be the value? This voltage drop referred to secondary, this value will be multiplied by the ratio of the number of turns, that is N2 by N1, or we can say K. As it is, any voltage is V2 by V1 is K, that is the amount of voltage that is K times more in the secondary. So this is a voltage drop. This is similar to a voltage. This will be, when this will we take it to the secondary, so this voltage value will be multiplied by turn ratio. As we already know, the voltage is proportional to the turns, so voltage will be either increased or decreased as per the, depending on the turn ratio. So we multiply it by turn ratio. This is the actually voltage drop. This same primary voltage drop, when we bring it to the secondary, the voltage drop become this. Now we want this voltage drop to be provided by x1 dash. So the in other x1 dash terms, the x1 dash into secondary current is I2. This is the voltage drop in the secondary. So this will be equal to, or this should be equal to this one, I1 into x2 into N2 by N1. So we want to find x1 dash, so that will be I1 by I2 into x2 into N2 by N1. So now this I1 by I2 is also, I1 by I2 is K into x2 into N2 by N1 is also K. So we get K square into x2. Not, this is not x2, this is basically x1. When this I1 x1 is referred to secondary, so this is I1 x1 into N2 by N1. So this is always x1, x2 is not there, so this is x1. So we see that x1 dash is nothing but k square into x1. That is, here we get x2 plus x1 dash becomes k square into x1. So when we bring everything to the secondary, the equivalent circuit becomes this one, or we can again draw this one. It becomes like this, where this is the total resistance, that is itself R2, it was there R2, and k square into R1 from this side, and the reactance again becomes, earlier it was x2 in the secondary, plus from the primary we get k square into x1. So this is the total reactance. Now this is V2, this is V1. So this is the equivalent circuit when everything is referred to the secondary, or we are transferring everything to the secondary. And case 2 will be if we transfer everything to the primary. So we can directly draw what will happen in the primary. So in that case, everything is in the primary. So primary side we will have actually 2 resistance and 2 reactance. So 2 resistance and 2 reactance. This is the transformer core, and secondary side nothing. So this one resistance is already there, R1, one reactance X1, and this is basically R2 dash. R2 is there, R2 is coming to here. So this will be actually R2 dash and this will be X2 dash. So basically R2 dash signifies that equivalent of R2 in the secondary, bring it to primary. Now in this case, what will be this R2 dash? Basically R2 dash will be, there we have multiplied by k square, and when from primary to secondary, when we are bringing secondary to primary, that will be divided. So R2 dash will be basically 1 upon k square into R2. Similarly, X2 dash will be 1 upon k square into X2. So now all parameters are known. So when this is the basically case 2, when everything is referred to primary, that is case 2 is everything is referred to primary. And I like to add one very small thing that we have already ignored in the discussion, that normally we can ignore for simple discussion, but at least for the sake of information we should know that there are two more things in the equivalent circuit that we generally ignore. Let's say here, we have seen this, and then the transformer, and this side this is R2x2 R1x1. So we have done this one, but we have left one small thing that we should, at least you should know, that there is something like this, one resistance and one reactance is here, right? So this resistance is known as RC and this reactance is known as XM. And this current is basically, someone call it I0, someone call it IE, and this current is basically IC and this current is IM. And just simply let me tell you what is this. This I0 is basically no load primary current, and this no load primary current basically used to compensate for the iron losses and coal losses. This IC shows the core losses. The IC, this I0 has two components. IC is the component that contributes to core, that actually this current is consumed for the core losses in the core losses, or you can say iron losses in the core. This is IC. So that generated as heat, so we show it as a equivalent resistance RC, where IC square RC, or the core loss component, will be IC square into RC. In the no load condition, the core loss remains constant in the no load or full load. So this is and this whole IO, sometimes called IO, in some book you may find it as IE, that is excitation current. And this IM basically is the actually magnetizing current. This is the current that actually creates the magnetic flux phi in the core. So this magnetic flux actually goes to the second other side of the limb core, and that the E2 is induced in the transformer. So this IM is the magnetizing current, which is basically, if you see in the phasor diagram, already we have discussed this one. So this IM is this side and this is the phi flux, and this will be actually the voltage V1. This will be E1, that is equal to minus V1. This will be E2 and actually this will be IO. It has two component. This is the IM component, not here IM, and actually there will be IC, another component. We sometimes say IW or IC. There will be this component, loss component. Sometimes we call IW, sometimes call IC. So this will be the actually phasor diagram, and this is the actually power factor. So this is actual real, but this loss, this I0 value is very less compared to the actual full load current. So we normally for all purposes we ignore all this part and we show only this R1x1 and R2x2. So it is for your information that there is something, but you should at least know only this thing. Okay, thank you. This is the transformer equivalent circuit. Thank you.